previous two theories that we discussed were related to the brittle material. Now we are going to discuss two theories that are related to the ductile material. So the first theory that is related to these ductile material is maximum shear stress theory, and it was proposed by Henry Tresca in 1868, and that is why this theory is also called as Tresca yield theory as well. The basics of this theory is that the material is going to fail when the yield stress of the material becomes equal to the maximum shear stress. Now, let's discuss this on whiteboard. For example, let us consider that there is a steel bar or a steel member on which this tensile load, let's suppose T is acting. Okay. So, on which this tensile load T is acting. Just give me a moment. So when this tensile load is being acted or is applied to this steel member, the material is going to fail. So in the experimental testing, it has been observed that this failure or the failure that is going to occur or the failure plane that is being formed is something like this one in the case of ductile material which is being acted upon or on which the tensile load is being applied. So these lines or the when the material is failed, it will have this 45-degree line with respect to the horizontal axis. Now these failure lines are called as Luder's line, and usually they were observed. And I think you are going to perform some experimental tests on these steel strips, and you will observe that this failure or type of failure shape that will be formed is at 45-degree with respect to the horizontal axis. Now, the this person Tresca proposed that this slip or this failure is due to the shear stresses. Now, why he made this assumption or made this hypothesis? There is a reason behind it. Now, let us suppose that we have this tensile bar which is being represented over here, on which these two tensile loads are being applied, and there is a small element in this tensile bar which if we see in the magnified view is something like this one. Due to this applied load, let's suppose the stresses on this element has approached this sigma y or the yield stresses. Now, since the load is being applied only in one direction, so obviously the stresses will also be produced only in the one direction, that is this sigma y. If I represent these stresses on the Mohr circle, obviously there is no stresses in this x direction, or let's say these stresses are equal to 0. Similarly, on this side, these stresses will also be equal to 0. So we have stresses only in the one direction. So for the Mohr circle, obviously one of this axis or one point or one coordinate will be the origin, and the other coordinate will be this point that is represented by this sigma y, right? So this will be the Mohr circle for this element which have been taken from the steel bar, right? In this element or in this Mohr circle, if I want to calculate the maximum shear stresses, we know that this is the axis for the normal stresses and this y-axis is for the shear stresses. And you also know that the maximum shear stresses will be this one. If I see from this figure, this maximum shear stress will be equal to this yield stress divided by 2, or it is equal to the radius. The diameter is equal to sigma 1, and maximum shear stresses is equal to the radius, that is equal to sigma 1, or I can say that it is equal to sigma y by 2. Now, what is the angle of these maximum shear stresses? These maximum shear stresses are acting at an angle of 90 degree, and we also know that if some stress are acting at 90 degree in the Mohr circle, then these stresses are actually acting at 45 degree in actual element or in actual plane. So this angle is 45 degree, right? So at 45 degree, we have the maximum shear stress that is acting, which is equal to sigma y by 2. That is why, now this was the reason. From this figure, you can see that the failure is occurring at a plane that is 45 degree with respect to the horizontal plane. And from Mohr circle, we can see that at this plane, which is 45 degree with respect to the horizontal, we have stress, that is maximum shear stress, and it is equal to sigma y by 2. And that is why this person Tresca said that the failure will occur when maximum stresses will be equal to half of the yield stress, right? So again, although it can be represented in this form, but in the previous two theories, you have seen that we have represented the failure in terms of principal stresses. So just to be consistent with the type of stresses we use, we will replace this tau maximum with the principal stresses as well in this theory. So how can we do that? Let's suppose we have this same element on which these maximum principal stresses are acting at this axis, that is sigma 1 and sigma 2. We know the equation of principal stresses or maximum stresses or maximum shear stresses, that is sigma x minus sigma y by 2 sine of 2 theta plus tau xy cos of 2 theta. Now there can be three possible cases. First case is that both sigma 1 and sigma 2. So the first case can be that sigma 1 is acting but sigma 2 is equal to 0, just like this one. And the second case is that sigma 2 is acting but sigma 1 is equal to 0. And the third case is that both sigma 1 and sigma 2 are acting collectively or at the same time on the material. So for the first case, obviously the maximum shear stresses are at angle of 45 degree. So this will be sine 90, which will be equal to 1, and cos 90 is equal to 0. So for the first case, we will have the equation for tau maximum equals to sigma 1 by 2, because sigma x is equal to sigma 1 and sigma y is equal to 0 in this case. Okay, so in the second case, for the second case, if we take the absolute value, that will be, because it can be negative or positive, but we are interested in considering the absolute value. Why? Because yield stresses that we are taking for the steel material are acting in one direction, or they will have an absolute value, so we can compare only the absolute value with the absolute value of shear stress over here. So if we take the absolute value, it will be this one. Similarly, for the case 2, we have T maximum or T absolute maximum equals to sigma 2 by 2. And for case 3, our equation will be, in that case, both sigma x and sigma y are acting, that are equal to sigma 1 minus sigma 2 divided by 2. And this factor will again be 0 because cos 90 is 0. So if I replace these equations into this original equation, I will get, for the first case, the equation is sigma this tau maximum by sigma 1 by 2. I will get sigma 1 by 2 is equal to sigma y by 2. Or these two terms will cancel out, and I have the absolute value. So this sigma 1 is equal to sigma y. And the second condition is in same way will be sigma 2 is equal to sigma y. And the third condition is sigma 1 minus sigma 2 is equal to sigma y. Now, just like the previous two theories, this is the same. In the same way, we will check for our material. We will calculate this sigma 1, sigma 2, and sigma 1 minus sigma 2. So we will check if these stresses are equal to yield stresses. If any one of these condition is satisfied, we will say that the material is going to fail. But if all of these conditions are not satisfied or all of these stresses are less than the yield stress, we will say the material is safe. Now again, just like I told you before, that we, if we can represent it in some graphical form, it would be convenient. We don't have to apply these equations all the time. We will just calculate sigma 1 and sigma 2 and plot these points on the graph, and the we will get the idea that whether the material is going to fail or not. So for this theory, the graphical representation is something like this one. Uh, for example, we had these equations, that is sigma 1 is equal to sigma y, sigma 2 is equal to sigma y, and sigma 3 is equal to, or sigma 1 minus sigma 2 is equal to sigma y. So sigma 1 over sigma y is equal to plus minus 1, just like normal stress theory. Sigma 2 over sigma y is equal to plus minus 1. Sigma 1 minus sigma 1 minus sigma 2 over sigma y is equal to plus minus 1. So this is the governing equation for this maximum shear stress theory. And if you plot this sigma 1 over sigma yp on this axis and sigma 2 over sigma yp on this y-axis, you will get this kind of failure shape or this kind of failure criteria or failure limit for this one. Now, if you calculate sigma 1 over sigma yp, and this shape, by the way, is also called as Tresca hexagon. Okay, so now you will calculate sigma 1 over sigma yp for your material and sigma 2 over sigma yp for the material. And if that point is lying inside this shape, anywhere, somewhere over here, then you can say that the material is safe. But if the point is lying outside this shape, you can say that the material is going to fail. Obviously, you can check it directly from these conditions as well, but just to have some convenient way, because if the material is a large one and there are like 100 of stresses or 100 of these maximum stresses, then it is not easy to check for each case. You will simply plot all these points in this curve and you can see that which materials are lying inside the shape and those points are safe, or those points are not going to fail, and the points which are lying outside this shape are going to fail, or you can select a different material for that one. The fourth and the last theory is for the also for the ductile material, and that theory is maximum distortion energy theory. So it is based on the principle of work done, just like we discussed in the case of in our structure analysis lecture, that the work done or the external work done by all the forces that deforms an elastic body is stored in the body as the strain energy. So if you remember, we wrote one equation in our that structure analysis course, then the external work done is equal to internal work done, and this internal work done is equal to the strain energy of the body. So this theory is based on this same concept. There are some definitions that we need to understand prior to moving on to this theory, that is the strain energy density. So the first definition is this one, and just like the density is equal to mass over volume, so strain energy density is basically the strain energy per unit volume at any point is known as strain energy density. And there are two types of this strain energy density. One is the volumetric strain energy, and it can be defined as the density associated with the change in the volume of the material. And the second one is distortion strain energy, and that is the density that is associated with change in shape of the element without changing its volume. For example, what does these two definition means? The strain energy density is obviously the strain energy per unit volume, but strain energy can occur both from change in volume or from change in length as well. So volumetric strain energy density means that when this strain energy is being produced, or when the strain energy is due to the change in volume, that is the volumetric strain energy. And distortion strain energy is when this change in strain is due to the change in length of the material, that is the distortion strain energy. So when does this failure occur, or what is the limit of this failure? Obviously, the scientists who proposed this theory said that the distortion strain energy of the material can be represented by this relationship. Obviously, we are not going too much into the details of this relationship. So he already gave us this relationship that the distortion strain energy can be represented by this formula. And this formula, this G, is obviously the shear modulus of the material. This sigma 1 and sigma 2 are the principal stresses. Now this UD is basically the internal energy or the internal work done of the material. But still we need to figure out that what is the external work done, or the external force, or the work done due to the external force which is being applied on the material. So we have been provided with the internal work done, and the failure will occur when the internal work done, that is represented by this UD, is equal to external work done, or the work done by the yield stresses, or the yield stress which is being produced in the material due to the application of the external force. So What is that yield stress, or how can we can figure out? It is uh, just a simple derivation for that one. Let's suppose we have again this steel bar on which these two forces, or let's say these tensile forces, are acting. Now, since these forces are acting in one direction or the uniaxial direction, so we will have, due to this tensile forces, maybe we will have some yield stress which are being produced at, let's say, at this point or at this section that is being represented by this sigma yp. And since it will be produced only in one direction, let's say in sigma one direction, so in that case, this sigma 2 and sigma 1 2 will also be 0. So if I substitute these values to calculate the internal work or external work done due to this yield stress, I will get, or this equation will be modified in this way, that 1 over 6g, obviously the yield or the yield stress will be produced in one direction. So this equation will be transformed into ud yp is equal to 1 over 6g. Sigma 1 will be sigma yp square plus sigma 2 will be 0 because the stresses are being acted only in one direction, and this factor sigma 1 and sigma 2 will also be equal to 0. So we have this equation for external work done due to this external force being applied. So if I replace this expression into this one, what will I get? Let's do it over here. I will get 1 over 6g sigma yp square is equal to 1 over 6g sigma 1 square plus sigma 2 square minus sigma 1 and sigma 2. So this factor will be cancelled out, and we have this equation, that is the governing equation for maximum distortion energy theory. So if you have a material and you know that what are sigma 1 and sigma 2, which are basically the internal stresses, and you also know the yield strength of this material due to the externally applied force, then if this condition is satisfied, or if this side or this factor is greater than or equal to the yield stress, then the material is going to fail. But if this right side is less than this sigma yp, then the material is safe. So again, if you want to represent it in the graphical manner, what will you do? Again, you will represent it, or you will show its nominal normalized form. And how can you get its normalized form? You will move this sigma yp over that side, or divide this this equation as a whole with sigma yp, and you will get this equation, that is sigma yp over. Now if this condition is satisfied, it will mean that the material is safe, but if this condition is not satisfied, it will mean that the material is not safe. Now if I represent this solution in the graphical manner, we will get this elliptical shape, right? This elliptical shape over here. Okay, so this is known as the failure criteria for maximum distortion energy. If this sigma 1 over yp and sigma 2 over yp are lying inside this graph or inside this elliptical shape, obviously the material is safe. But if these points are lying outside this elliptical shape, the material is going to fail. And you can see there is a difference. Both these theories are being applicable for the ductile material. Now this hexagonal shape was for the initial theory, or the Tresca yield theory that we discussed. Now you can see that this theory is giving us a bit safe edge. So for example, if a point is lying somewhere over here, this sigma 1 over yp or sigma 2 over yp, if a point is lying somewhere over here, then this point, or this point in the bar, if we are considering a bar, then this point in the bar is going to fail according to the Tresca theory. But according to the maximum distortion energy theory, this point is safe, and we don't need to change the material, or we don't need to apply different materials. So again, just like I told you initially, that different theories will give you the different results. So it is a general practice to check the failure of the material based on all these theories, and even if it satisfies, or even if it is being deemed as safe by one of the theory, we can consider it as a safe material, or we can consider the stresses at that particular point as safe, and we can proceed with the calculation. Now let us solve one. So this is all about these four theories, and let us solve one simple example just to get an idea that how these theories work. So for example, let's suppose that we have this solid shaft of a radius of this 0.5 inch, and it is made of steel having a yield stress of 36 ksi. The shear stress is also given to us as 617 ksi. So the shear stress is 17 ksi, and we need to figure out that the loadings due to these shaft or the stresses which will be produced due to these shaft at this point A will cause failure or not according to the maximum shear stress theory and the maximum distortion energy theory. So let's apply this, or let's solve this question and see what can we get. So for this material, we have been provided this tau xy equal to 17 ksi. We have been provided with the load that is P equals to minus 15 kilopound because it is being applied in the compression side, and radius has been given as 0.5 inch, and we need to figure out that at a point A, which is somewhere at the center, or at any point on this shaft, the failure will occur or not. So what is the first step? That is obviously the calculation of sigma x or the normal stresses. So we have been provided with this force P, and we know that the stress or sigma x will be equal to minus P over A because, or let's say it is plus P, and the minus sign will come from here. So sigma x will be minus 15 over what is the area, that is pi r square. So if I substitute the values, I will get minus 15 over pi into 0.5 square. So sigma x is equal to minus 19.10 kilopounds per square inch. So we have this sigma x, we have this tau xy which was given in the question, and now we can calculate this sigma 1 and 2, and then we can apply the theories of failure. So if I represent these stresses on this element, I will get that is 19.0. This stress is obviously 0, that is sigma y, and from here we also have minus 19.0, and the shear stress is as 17 ksi. So this is the shape of the element. Now if apply, or if I, because obviously to apply these theories, I need to find out sigma 1 and sigma 2. And the equation for this was sigma x plus sigma y, if you remember, plus minus under root sigma x minus sigma y divided by 2 whole square plus tau xy whole square, right? So if I substitute the values of sigma 1 and sigma y, I will get sigma 1 and 2. So sigma x is equal to minus 19.10 plus sigma y is 0 divided by 2 plus minus 19.10 minus 0 divided by 2 whole square plus tau xy again is 17 square. So if you solve this equation, you will get sigma 1 is equal to 9.56 ksi, sigma 2 as minus 28.66 ksi. So now you have this sigma 1 and sigma 2, and it was asked in the question to check the failure criteria based on maximum shear stress and maximum distortion theory. So according to maximum shear stress, we have three criteria. That is, sigma 1 should be less than equal to sigma y. The second is sigma 2, or the absolute value you can say, should be less than equal to sigma y. And the third criteria is that sigma 3, or sorry, third one is that sigma 1 minus sigma 2 should be less than equal to sigma y. So what is sigma 1? Oh, sorry, sigma y, it was given in the question as 36, the yield stress. So sigma y is given to us as 36 ksi. So sigma 1 is 9.56. So we can say that sigma 1 is less than or equal to 36, so the material is not going to fail. The second condition, obviously sigma 2, that is equal to minus 28, and again it is less than or absolute value is less than 36, so it is also equal. And the third condition is that the difference between sigma 1 and sigma 2. So sigma 1 is 9.56 and sigma 2 is negative, so they will add up 28.66. So are they less than 36? So if we add them, we will get 38.2 less than or equal to 36. So this condition is not satisfied. That means the material is going to fail according to the Tresca theory or maximum shear stress theory. And the second theory that we need to apply is the maximum distortion theory. So the condition for that one was that this sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square should be less than or equal to sigma y square. So if I substitute the values, I will get 9.56 square minus 9.56 into 28.66 plus 28.66 whole square. It should be less than or equal to the square root of sigma y, that is 36 square. Right. So if you solve this one, you will get 1187 less than or equal to 1296. So that means that the material is safe and is not going to fail according to the distortion theory. So just like I told you in the slides that it is quite possible that the material will fail according to the shear stress theory, but it may be safe according to the distortion energy theory. So you have seen that in the example problem. So this concludes our lecture for this failure theories, and this lecture is important with respect to the objectives. So you should know that what are the governing equations or the governing shapes for these theories, and even these type of problems can see them in the objective, or maybe short questions can be from these theories. So at least try to just revise these slides or look into these slides, and if you have some questions you can obviously connect me at